type. And once that's done, you can drag this one to near the profit one. And you're going to see this one. It's right here. It's much, much better than this one. Than this one. I mean, it's the same. It's 30%. It's 30 point. It's the same, but it captures more refined details. That's something I would call like forecasting. I'm going to show you another real example. How I did that. I mean, when you have data like lots of fluctuations, and your forecasting model should cover all of that rather than it's like centralized. So this is a much better approach. You want to try, or you want to see the next one? Next one. Okay. Then what about the percentile? So percentile, let's say we have sales. I mean, if you can go to this one worksheet, it's a percentile-based prediction. And this is how you create syntax for percentile. So you have like 3 options for model. You have like numbers for percentage. You have target expression. You have predicted expression. But the difference between percentile and quantile is that percentile means, so this line is actually represents the percentile number you specify, like maybe it's 8% or 80%. So any dots above, let me show you something else. Like you want to find some outliers. Let's say you want to find some outliers. 60 is not good for, let's say, 95. So 95% is a good way to identify the outliers. When the number is going far away or going like too low, and you have a criterion to identify that. So in this case, you can tell your audience that, hey, this part above this line, you could take that as outliers. Or you want to find outliers near the low level, you can also do that. Like you can try like maybe 5%. So this one here, you can treat that as outliers. So basically, it's a line that's trying to represent the common trend by help you detecting, what is a straight point. But I wouldn't think this is a good one because here there's a lot. So I wouldn't think this is a good performance. Anyway, this is only 2 functions provided by Tableau for predictive modeling or analytics so far. I wouldn't be satisfied with this one because for giving a representation to the business level, it's okay. But once it's something like it's really something application you have to develop, then you just have to try something else. The reason I have to try this, I have 2. We'll call that 2 reasons. Because I heard from some of you that this is not the only course. You also have other courses. Maybe you're doing analytics, math, regression. You have some final project. you need do some modeling or regression, which is part of that, not all of that. And you don't know how to move forward with that. And I can give you some example. This is an example. I'm trying to show you that that's a real world application which going far, far way beyond Tableau. And also, this is something showing that you have to try something else. This Tableau, working together. Why we have to have them working together? That's going to tell us the reason. So this is just a case study I would like to share with all of you. That's back to, I think, almost 10 years, no, 9 years. It's quite a while, but the model still works very good these days. So I was given a project trying to forecast the number of phone calls. It was like during winter time, somebody gonna just pick up phone call, the call center. Hey, it's big snow, or it's very ice outside. So the call center received lots of phone calls requested by the citizens. They need some service for can you just clean up the snows, or it's too dangerous, something happened there, we need your help. A lot of different types of service, but all those services are relevant with winter situations like snow and ice. So my challenge is that the factors are changing a lot. Like every day, the value changes so fast. And the requirement is that the client, I was asking the client, why do you want the number to tell you that? And their answer is that our human resources are limited. We want to forecast the numbers for tomorrow, for next week, so we can prepare. We don't have to, assign 10 or 100 people to prepare for picking up the phone calls. It depends on your forecast. Maybe just, we only need 20. Or you want to have a clear idea, you see from a weather forecast, in 2 days, it's going to be snow, heavy snow. How can we prepare for that? I need a clear number. Are we going to receive 100 phone calls or 100 phone calls? Depends on that number, so we can prepare for a human resource. So that's my job, to develop a forecasting model, and that might be similar somehow to your project, or don't have to be. Or in the future, you might have similar project. You want to forecast something based on a lot of factors, like 20 factors, not just one factor. Of course, one of them has to be time, but others can be a lot of different things. So I need to model the cause effect. What I can get for a factor is except time. I have to consider a lot of other things like weather. The weather can have a profile of data sets like temperature. You don't have to take a picture. Mean temperature, precipitation, dew points. Like you can check those open source weather outside. We have something called open weather. I can put down every day. It's open source. So they give you some JSON file for every day's forecast and also yesterday's forecast, telling you that what is maximum temperature, what is the lowest temperature, and humid, the precipitation. If the snow, like for yesterday, how big it is, what's the volume for that snowfall. I think all those factors are interesting and they're helpful, but I need to model the contributions from those factors to the number of the phone calls, right? So this is a regression. Clearly, this is a regression because the number of the phone calls can be like 200, and I need a curve. And I need, like I was told, hey, I want next week, only 7 days. So you have to tell me
on the Monday, you have to tell me what's the number for Tuesday, Thursday, Wednesday, for how many phone calls we're going to receive, or call center. But like factors are factors. I also have to consider about their type-related context. So I think yesterday, like the snow fall there, definitely going to change or affect today. So if we have a lot of snow yesterday, or the day before yesterday. And about ice, that's a different story. Once the temperature is going down, it takes time to get the road freezing, right? It takes time, maybe yesterday or the day before yesterday. So those factors going to form out some contributions to today or tomorrow. So that's why I introduced the previous. So previous time. So I'm not just checking how the winter situation looks for today. I'm going to check all of them for previous day, 2 days ago, or 3 days ago. So all those things come up, forming a big set of factors. Imagine the number, like if you have those factors, you can check the complexity of it. So that's some of them. It's crazy, I know it's crazy. Previous time, like say yesterday I received 10. Okay, I also think that's going to be a factor. Like yesterday was 10. Whether that's going to be introduced something for today's phone call. 2 days goes count. And what is months? Like winter, the months of winter will be different from summer and the spring. So all those things, I have like 20 factors, and your computer going to make a lot of combination. So for 2 of them, 1 of them, 3 of them, 15 of them, until 20 of them. How much going to be the combination, the permutation? 1 million. That's a number I have to try. I know it's crazy, but that's a real world application. I have to deal with it because I mean, given those factors, I'm not sure which of them, or which 2 of them, or which 5 of them, gonna make the best model for me. So I would like to try all of them. Why not? Because I have a super powerful computer. So let's do that. I want to try Mullen regression in this way. So this is how my regression platform works. I have a distribution engine in the beginning. And that is going to try 1 million solutions. By 1 million solutions, I mean every solution is a factor, right? 2 factors, 3 factors, but it's going to be like shuffle around. So this is just like 1 from to 8. And I'm also going to try different algorithms, like, multiple polynomial regression, that's something you can get, or support vector machine, that's super small but very good, or decision tree, it's tree-based regression, or random forest, you have lots of trees, like 200 trees. Every tree is going to make a decision, and then you're gonna wait out. So I have lots of algorithms, I have lots of factors that's going to even make this regression getting more and more time-consuming, energy-consuming. So I have to distribute that to many CPUs. I have many CPUs. I have like 64 CPUs. So I distribute that computation to 64 CPUs and leave that run for a week. It's heavy. But then you have something you're going to have to bother. For those 1 million solutions, as a candidate, how can you identify which one is the best? You have 1 million, just based on score. Let's say you have regression accuracy, right? Just based on the top one, can you think that is best solution or not? Naively think, I would say, yes, I could try that one, but no. when you look at your data, I'm just curious. So this one is how I do machine learning from the previous 5 years, from 2006 to 2010, and use that to train my machine for this 1 million solutions. I try this model with test. By test, I mean that's new data. I mean, although for us right now it's not new, but for 2010, it's new data, right? And I generate some candidates, and I do the same thing for different slots. And I want to find which one is most reliable. So if the one is reliable, it should give always good results, right, for different years. So if some of them, the resolution, the candidate from the first one, if that's really working, then that should be working for all those different things. So we are trying to find overlapping. So I do get through all of them. I find overlapping is this part. See this dot? So that means this dot, it represents a solution, a regression solution. It's working for all those scenarios. So that's the one I would call that the reliable ones. And then I have to try these ones. Now there's some interesting demo there. So for the overlapping part, I find from 2011, that's 3,000. And right here, they use it have different color, which is also classroom. I mean, it's a classroom. So different color, which means different factors. And you could say and this is the regression accuracy. So I use a correlation. So right there, so that one, the top one, might be good. But this is for the solid level. So I do the same thing. We try to find the overlapping stuff. So for the second experiment, I have more. I have 16,000 candidates. And this is the third one. This is the last one. So that's a stable. Candidates are fine. So that's stable. We can go back to here. So this part, finally generate around 300 solutions. All those ones are reliable ones. I mean, regardless their accuracy, they're reliable. By reliable, again, I mean all those solutions, if they're being used to predict different years, their performance are stable. It's not like for this scenario is going up a lot, for this scenario is going down a lot. No, it's always stable. And then from there, then it's the moment for me to rank. I'm gonna go this one, or probably over there, as the final candidates. So finally, I divide. This is a fixed set. I'm gonna deliver that to my client. So my function have these factors. So weekday measures, snow count measures. So snow count, which means how many numbers you get snow from historical days. Previous dew point, I don't know why that matters, but it's strange. It's there. It definitely has its own reason. And I try this random forest with these factors. That gives me the best result. You could have your own regression algorithm, like linear or logistic regression, or all those different regression tools. But the thing is, in theory, your algorithm always work a little bit. But would your client accept that? It depends on how much accuracy you achieve. Like one of my client, one of my colleague, sometimes deliver modeling. Like, hey, this is 60% R2 squared, R squared. But the clients think, and then say, it's 60, but it's okay, it's acceptable, but not the best. But if I can come up with a model telling them, hey, this is 82% of R squared, you can love it. So in theory, the algorithm can always be applied, but we do bother with your regression performance, which is about accuracy.